Okay, this lecture we want to get into the mathematics of quantum mechanics, and we want to see from what we learned before about our plane wave state, we want to see how we can get to a wave equation for objects that we traditionally think of as particles, like an electron. That's usually the typical example. The way we're going to do this, though, is we're going to look at Maxwell's wave equation and talk about the wave function for a photon, see what we get, introduce some new mathematics that's actually central to quantum mechanics, and then we'll return to see how we can do this for an electron in a later lecture. So right now what we want to do is look at Maxwell's wave equation, see if we can express it in a different way. So recall, here are Maxwell's wave equations. We have the electric field component and the magnetic field component. To keep things simple, we're going to stay in one dimension, and we're not going to worry about the magnetic field component. We're just going to look at the electric field component as we go along. And we talked about the solutions, and we talked about essentially the plane wave state solutions. That's what we really want to get towards. But recall, we had two types of solution. We had a cosine solution, which if we plugged in this form here, e x t is equal to e naught cosine x of t. Now again, e naught should be a vector, but we're just going to be, we're not going to worry about the polarization here for the moment. We just want to look at the types of solutions. And we take two derivatives, we get minus cosine back with pulling out the coefficient, which is k squared. So it's minus k squared times the original E field back. And it's the fact that we're getting the original E field back that's interesting here. For the time component, we take one time derivative. We get negative for that, and we pull out a minus omega, so that's positive. We take a second derivative with respect to time, we get minus omega squared, with the original electric field component. Yeah. And we see that's essentially the two sides or the two components of this equation. And we would see that this would be a solution, or it is a solution, as long as we have omega is equal to kc. So if omega is equal to kc, then this will satisfy this equation. So that's the simple cosine or sine, stick in a phase factor, solution to this equation. Now, what we want to really look at is another type of solution using the Euler relation. So if we use the Euler relation, recall, I assume you're familiar with this, that e to the I theta, a complex exponential, is equal to cosine theta plus I sine theta in general. We can rewrite a solution as a complex exponential. So we can consider another solution of the wave equation as such. The electric field component is equal to E naught, the amplitude, e to the I kx minus omega t. Now, a few words here. In classical optics, you will often consider solutions like this for the electromagnetic wave or component, electric field component. And you say, well, in real classical physics, we don't have imaginary functions or imaginary observables, so why is this allowed? Well, the trick in optics is the following, is that you can do this in classical optics, forget about quantum mechanics for the moment. You can use a complex exponential like this, but at the end of the day, when you want to find the functional form at the end, you take the real part of it. And that's just by taking the function added to the complex conjugate of the function, which the complex conjugate only do is take I and minus I and divide by 2. That gives you the real part of that function, and that is your actual answer. So in optics, it's a mathematical trick, if you will, to actually find solutions, and it saves a lot of work. And we'll see now, in this case, and others as we go along, that using complex exponentials is actually very nice. And as we'll see when we get to quantum mechanics proper, we have to use complex exponentials when we get to electrons, for example. So let's carry out the math here. Let's just do the x derivative first. We have that derivative x pulls down the coefficient for an x, which is ik. But notice that the E field itself, the E naught e to the I kx minus omega t, doesn't change when we take a derivative. That's the nature of an exponential. So when we take two derivatives, we just pull down that coefficient squared, which is ik squared, and we get minus k squared times the function back, just like we had before. The time derivative is the same thing, but we pull down minus omega squared, that component squared. And again, we have, if we write out the wave equation now, we have this form, and we can cancel the E naught and the exponential terms. And again, just as before, if we have omega is equal to kc, then this will be a solution. Now, again, in general, we want to be careful and we want to consider the full vector nature of the solution. We're not going to, but here's just a simple case just to get at the heart of the matter, which we really want. Okay? Now, let's look at another case. So what we want to do now is consider, let me remember this. Let's think about this now in terms of the wave function. And we're going to still talk about a single photon. And there's some caveats there, but we'll talk about a single photon for the moment. And what we want to do is rewrite the plane wave state, which we just introduced, in a different way. But first note that the wave function psi is going to be some amplitude A, e to the I kx minus omega t. So this is essentially the same thing we just did, but now we're expressing in terms of a wave function. So we're going to use the de Broglie wavelength here, lambda is equal to h over p, and rewrite that by putting factors, dividing the top and bottom by 2 pi. We get the momentum p is equal to h bar k, and then solve for k. So k is equal to p over h bar. And we'll also use the Einstein relation, the E is equal to hf, what we found for the photoelectric effect that we talked about, and multiply top and bottom by omega again, or sorry, by 2 pi again, and we get E is equal to h bar omega. And again, we can solve this for omega, and then we'll stick it into here and here. When we do that, we can rewrite this complex exponential as such, as e to the I over h bar, getting rid of those common factors of h bar, px minus et. So this is the same essential form, but in terms of momentum and energy. And this is where things get interesting in quantum mechanics. Is as soon as you tie wave number or wavelength to momentum and angular frequency to energy, this is where you start talk about this weird nature of these functions, because it's in terms of energy and momentum. Now again, this function says that it's a definite state of momentum, p, is a definite state of energy, e, where x and t are the independent parameters here. Now what we want to do is take a derivative of some function. We'll take this function, and we want to see what we get. So let's take a function of this plane wave state, which is a special state because it has definite energy and momentum, and see what we get. So if we take a derivative with respect to time, we have the a out front, the amplitude, and we pull down the coefficient in front of the t, which is I over h bar minus e. So we have that I over h bar minus e times the original function. That doesn't change. And notice that's just minus I over h bar times our original function psi. This nature that we do some operation on it and we get the same function back is of a special form that we're really going to be, what we want to kind of introduce here, and it's central to quantum mechanics. But we need to get the same function back, but we'll come back to that. But this is all interesting in that, but notice if I do the following. Let's say instead of doing an operation of taking a derivative with respect to time, I do the following operation, which is very closely related. I take the derivative with respect to time, but then also multiply by IH bar. So if I do that, the IH bar, what it does, it takes the minus I to I, and it gets rid of the H bar. So when I do this operation, this mathematical operation of taking derivative with respect to time and multiplying by IH bar on our plane wave state, I get the energy of that plane wave state multiplied by that function back. So the way we say this, again, taking the operation, we get the function back. And so what we want to do is again, introduce now the notion of a mathematical operator. And this is kind of central to the mathematical structure of quantum mechanics. So we want to consider this new thing in parentheses here as an operator. And we're going to give it a special little symbol to identify it as an operator. We're going to give it E with a little caret on top. We do this in introductory physics courses just so we can distinguish between ordinary numbers and operators. When you look at more advanced quantum texts, you have to, it's clear what is what. And the mathematical operator E with a caret, or we'll call it the E operator for the moment, is the function here. It's not a function though, it's IH bar partial t. But notice that this operator, E, is not a complete mathematical statement, because what does partial t mean? It doesn't really mean anything by itself. It has to act on a function. And we call this, now in the parentheses, I'm going to call it linear Hermitian operator. So this is an operator. And just for now, we'll call it the E operator. I don't want to call it the energy operator for the moment, but we'll see. Well, I'll explain why in a minute. And again, the important thing is that operators by itself doesn't have a complete meaning. And those also, because of the nature of the derivative, this one acts from left to right, acting on a function in the standard way. The way we say this now is that the plane wave state is a special state that has a definite energy. We said that above because E in this particular original function here is a constant. And the way we say this now in our new mathematical, the new mathematics here, is that the plane wave state, psi, is an eigenstate, or sometimes called an eigenfunction, of the energy operator, or E operator, E with a caret on top, with eigenvalue E. So again, so E is, this is a scalar number, that's the energy of the wave function. And these are just, essentially, I'm just introducing terminology here, that's all I'm doing. But psi, and then again, psi has to have this special nature, not any function can do this. It's when you operate on it, you get the same function back, but multiply by some constant, say. That's what's called an eigenfunction or eigenstate. If I say, had an operator say x, multiplied psi by x, that would not be an eigenfunction because x times psi is not the same as psi because x is the independent parameter here. Okay, now this said we identified this with the energy of this particle, and I want to kind of constrain that in a minute, but so I'm not going to really call it the energy energy operator. It's an energy operator here, eigenvector. It's only in this case where the energy is constant. There's another operator, H, what's called the Hamiltonian, which is the proper full energy operator that we'll introduce later. So this is only a special case where this is equal to this, but we'll come back to this in a moment. Okay, now what we want to do is to look at, oops, 1 minute. What happened here? Look at, oops, I have the wrong, there we go. So what we want to do now is look at the following construction. Instead of talking about the energy, let's talk about the momentum. So, or just take a derivative with respect to x instead of taking a derivative with respect to time. And notice in this case we pulled on the coefficient in front, which is IP over h bar. Now I can introduce the new operation of taking derivative with respect to x, but multiplying by minus ih bar. And notice what I do, I get rid of the I over h bar. And so doing this operation returns the momentum of the photon multiplied by the function itself. So likewise, we define, now here we'll call it the momentum operator. And it's going to be, we'll use capital P. I gotta get rid of this thing. We'll use capital P, and it's going to be minus IH bar partial x. Again, by itself it doesn't have complete meaning, but it will return the momentum if it's an eigenstate of momentum, which again, the way we want to think about this wave function for this particular plane wave state, which is a very particular state, has a definite value of momentum, has a definite value of energy, and operating on it with these operators here, pull down, give those values for the momentum and the energy. And so what we want to do is, so now we've just introduced this E operator or energy operator and momentum operator. We want to use these in the next lecture to see how we can rewrite Maxwell's wave equation, but we'll do that in the next lecture. For now, what I'm going to conclude here just with a little bit more formal discussion of some of these terms. And we'll probably have another discussion here of the more formal aspects of the these notions. So in general here, what we want to introduce here is the terminology I just used, and we're going to call this an eigenfunction, eigenvalue equation or relationship. Eigenstate or eigenfunction is sometimes interchangeable. And again, particular feature of this type of expression is that we have an operator acting on an eigenfunction, and it returns an eigenvalue, which is a scalar number, times the eigenfunction back. And we have to return the same function. If we don't return the same function, this is not an eigenfunction-eigenvalue relationship. So operator times eigenfunctions is eigenvalue times eigenfunction. And again, abstract or just in formulas, some operator omega acting on some function, eigenfunction f, returns and a particular eigenvalue, which will depend on the state that f is in, times that function back. Okay, quickly, just to give you an example. So this is not, you're not meant to understand this example, but this is one we hope to get to later, how this will use. And this comes in probably the most ubiquitous problem in all of quantum physics, and that's the harmonic oscillator. So I won't go through all the details here, but I'll just introduce what we'll call the Schrödinger equation, but which is just the energy equation here. And we have an operator here, H, which is called the Hamiltonian, and it will give the energy. And the energy will be E sub n, where the n indicates which state it's in. Now, again, this is sort of like the Bohr model, where we have different energy levels for an electron and orbiting proton and a hydrogen atom. In a harmonic oscillator, the particle can be in different discrete, we'll see, in energy levels, and n indicates which level it is. So we say that psi sub n is the eigenstate or eigenfunction for the particle in the nth state, which has energy E sub n. And again, in case you just want to know, the energy in this particular case turns out to be n plus a half h bar omega, where n runs from 0 up into infinity. And it's an integer, of course. Okay, lastly, I want to conclude by just clarifying a little bit those two terms I used before, linear Hermitian. What are those? What does that mean? But again, linear Hermitian operators are central to the mathematical structure. And I just want to kind of give a little bit, and we'll come back to this later in a little more depth, what they are. But linear, actually, we can explain completely. Linear means that if the operator acts on a sum of two functions, for example, that will equal the sum of the operator acting on each individual function. So as shown here. You can think of a case where that wouldn't work, is to say the operator actually takes the function and squares it. That's nonlinear. In that case, if you did this, you get f squared plus f1 squared plus f2 squared plus a cross term. That would not equal to f1 squared plus f2 squared because you're missing the cross term. So that's what we mean by linear. And all these operators in quantum mechanics are going to be linear. Hermitian, there's two ways to address this. One is the mathematical nature, which we'll get to later. But really what we care about, the physical thing, is that Hermitian operators have real eigenvalues. So the energy up here, this is a real number. The momentum is a real number as well. And so it's the special mathematical property, nature of the Hermitian operator that will actually, that gives us real eigenvalues. And that's what allows us to correspond them to physical properties, because whenever we measure a physical property out in the world, it has a real value. We don't have complex energies or momenta, for example. So this is why Hermitian operators are special in this sense. And we'll talk about the mathematical meaning later. We'll come back. Just as a side, there is some current research in the last several years about a small class of operators that actually are not Hermitian, but actually do have real eigenvalues. There's still a question whether those are deemed physical or not, but there are some operators which, constructed specially, will have real eigenvalues. It's kind of an interesting little thing. But we're not going to worry about that. That's kind of current research, but we will forget about that. But again, we will be talking about Hermitian operators. We'll introduce what the meaning is of those, hopefully, shortly.